we are going to study about the generalized circuit constants of transmission line. What will be the model which we discussed, that is short transmission line, medium and long transmission line. Now how to simplify the calculation using the generalized circuit constant, that we are going to see. So the generalized circuit constants are, there are four parameters are there. There are A, B, C and D are the parameters. So here you can see that we're using two equations. One is Vs is equal to AVR plus VAR and Is is equal to CVR plus DAR. Using these two equations only, we are going to find the ABCD constants for various set of transmission line. So here A and D have no constants. There is no unit for A and D. The unit of B is ohm and unit of C is mho. So these are the arguments we discuss. Coming to the ABCD parameters, always after forming the ABCD, we have to check that there are two conditions to be satisfied. There are two conditions to be satisfied: A equal to D and AD minus BC equal to 1. Okay? These are the conditions we have to satisfy, so that the corresponding parameters we can able to check. In the corresponding, see here, first for the short transmission line, for short transmission line, Is is equal to IR, Vs is equal to VR plus IR into Z. So here, how we are getting this equation mean, based on the current and voltage equation, we come across that we have to convert the each and every equations into this form. Vs is equal to AVR plus VAR, Is is equal to CVR plus VAR. In this form, we have to convert it. After converting that, compare with the short transmission line expression and then find what is the value of A, B, C coefficients. After by doing that, by comparing these two expressions, A equal to 1, B equal to Z, and C equal to 0, and D equal to 1. These are the expressions we are getting for short transmission line. Then, after this, if we go and check whether A equal to D, yes, that condition is satisfied, and then AD minus BC is equal to 1, and that condition also getting satisfied. After getting these things, now we can use this ABCD constant to find the voltage regulation and efficiency. Then coming to the medium transmission line, in medium transmission line, directly we are starting with nominal T method. The reason is, in nominal T method, in incandescent method, both the conditions are not satisfied. Even though A is equal to D there, that AD minus BC condition is not getting satisfied over there. So that is the reason we can't able to use or frame the ABCD constants for a incandescent method, in medium transmission line for incandescent method. And coming to the nominal T method, nominal T, you know the final expression, compare with that, this is the equivalent circuit for that. Compare the equations, and there you have to get A equal to D equal to 1 plus Y into Z by 2, and B equal to Z into 1 plus Y Z by 4, C is equal to Y. These are the expressions we are having. Then for nominal pi model, these are the expressions. Once again, using these things, we can able to find the voltage regulation and efficiency. Yes. Yeah, in long transmission line, already the equation is of the form of Vs equal to AVR plus VAR. AVR plus VAR. So that what happens means, if you compare these two, if you compare the A equal to D and B, AD minus BC equal to 1, all those equations, we are getting the expression for this. That is why we have we can able to use this long transmission line also. Yes. So these are some of the numericals which we are not going to discuss now. Just to apply how to find the corresponding voltage regulations and efficiency of the various cases, etc. Yeah. Next topic is, so far we discussed about the modeling of transmission line. The model, there are three models I said: short transmission line, long transmission line, and medium transmission line. In all these models are purpose of all these model is to find the efficiency or transmission efficiency and voltage regulations only. Okay. So with this, almost in long transmission line, using a rigorous method, we can able to find the regulation and efficiency which is almost closer to the theoretical line. Yes. Coming to the corona. So this is the important thing which is occurring in the system. The definition of corona is, there is a violet glow, hissing noise, and production of ozone gas. Why we need to worry about the corona? There are some advantage and as well as disadvantage in the corona. See, corona is due to ionization of air surrounding the conductor. An alternating potential difference is applied across two conductors whose spacing is large. As compared to the diameter, there is no apparent change. That means if there are two conductors operating at two different potential. In between that, air will act as the ionization medium. So what happens means, if the distance between, that is said to be D, if the distance between the two conductors or span distance If it is more when compared to the diameter of the conductor, then what happened means there is no apparent change in the conductor. So because of this, what happened means there is no occurrence of corona. But at the same time, because of some reason, because of some disturbance or practical reasons, we can't able to maintain always the span distances. Maybe in the turning of the street or somewhere you have to cross the road, etc. In that case, what you have to do is we can go for reducing the span distance. Definitely, if that is the case, the air which is between the two conductors will get ionized, and there is a possibility of corona. So this corona, when it is occurring, there are two different voltages are there. One is called critical disruptive voltage. Let us say your operating voltage is 11 kV. So up to 11 kV, there is no formation of corona. Maybe due to some reason, your voltage may be increased a little, maybe 12 kV or 12.5 kV like that. In that case, there is a possibility of corona. And the corresponding voltage where the corona starts occurring is called critical disruptive voltage, and the voltage at which it will be appearing is called visual critical disruptive voltage. There are two voltages are there. One is critical disruptive voltage, other one is visual critical disruptive voltage. You can see this. When the applied voltage exceeds a certain limit called critical disruptive voltage, the conductors are surrounded by a faint violet glow that is called as a corona. Okay. This phenomenon of violet glow, hissing noise, and production of ozone gas in an overhead line is called as corona. This will not occur in a cable. This is only the effect is only in the transmission. Yeah. For normal condition, this is the phenomenon behind the corona, how it is occurring, or how ionization happened, what happened to how this ionization process started, how the free electrons strike the neutral molecules and ionized, and how the process of corona is getting started. Yeah, these are the various factors which are affecting corona. If you see that there are 4 factors which are affecting the corona. The first one is the atmosphere. Yes, obviously because of the atmospheric climate condition, in stormy weather the number of ions is more than the normal, and such corona occurs at much less voltage. Even if you are saying that critical disruptive voltage, due to atmosphere, even at lesser voltage itself, there is a possibility of corona. The next one is the conductor shape. The shape of the conductor is the matter. Suppose if it is a polished surface, the occurrence of corona is somewhat less. If it is a rough surface, then the possibility is more like this. And spacing between the conductor. If the spacing between the conductor is more, as I said earlier in the previous slide, the occurrence of corona is less. If the spacing is less, then the occurrence is more, like this. The line voltage, line voltage greatly affected. If you go for higher voltages, there the possibility of corona is somewhat more. These are the various factors which are affecting the corona. And the main the thing is, there are 2 voltages are there. We need to find it. One is the critical disruptive voltage, other one is the visual critical disruptive voltage, which is represented by a symbol V suffix C. V suffix C is the critical disruptive voltage, where G naught R into ln of D by R is the formula to find it. Where G naught is called the potential gradient, and that is 30 kV per centimeter maximum. For a conventional system, the G max value is 30 kV per centimeter. That is a value. If you want to convert that into RMS, then it is coming around 21.2 kV per RMS is the corresponding value. So that G naught you have to find it and substitute there to find the critical disruptive voltage. See, here there are several factors we need to consider while finding the occurrence of corona voltage. So in that case, you have to go for del, where del is the air density factor. And the factors we discussed that there are some 4 factors which will cause the corona occurrence much sooner, like that. So in here also Vc is G naught and the del R into ln of dVr. Del is 3.92 B by 273 plus T. Using that formula, we can able to find the corresponding value that is there, critical disruptive voltage. Then using that formula, the surface also we discussed. The surface parameter is m naught, where m naught is equal to 1 for a polished surface. More the dirty surface or more the corresponding thing, the corresponding value is less. So like that I can say. So that is the critical disruptive voltage. The visual critical voltage is a voltage slightly more than the critical disruptive voltage. Visual critical voltage is a voltage which is slightly more than the critical disruptive voltage. So this is once again the formula for finding the visual critical voltage. Both the voltages are required to design the transmission line so that there is a less possibility of corona occurrence. Yes. Coming to the power loss. Before that, is there any drawback due to occurrence of corona? Means yes, there is a power loss. There is a power loss due to corona. since there is a power loss in the transmission line, unnecessarily due to corona, we need to see that how the possibility or the frequency of occurrence of corona as much as possible, we have to reduce it. So this is the formula, this is an empirical formulas. All these three formulas, visual critical, critical disruptive and power formulas, no need to go for the derivation. All these formulas are empirical formulas, just we have to take it as it is. These formulas are based on their experience and practice of the power engineers. It was done. Yes. Then a drawback of corona, just as we discussed, there is a loss of energy. Ozone is produced by corona, may cause corrosion of the conductor itself. And the current drawn by the line. Since there is an arcing formed, the current drawn by the corona is non-sinusoidal, and non-sinusoidal voltage drop occurs in the transmission line. This may cause some inductive interference related to some communication line. If it is there nearby, it will be happening. But here I didn't mention about the advantage of corona, but even though there are some advantages, what is the advantage of corona mean? Let us say there is a lighting strike in the transmission line. That lighting strike, what happen mean, because of that more amount of voltage, if it is a 11 kV transmission line or 22 kV primary distribution line, in that case what happen mean, there is a huge voltage will be traveled in the form of traveling wave, and that voltage will form a corona, and that traveling waveform will go and hit the primary winding of the transformer. Suppose before this, if corona get formed, the entire traveling wave as well as the current of due to corona will be dissipated in the form of arc, so that the intensity or the amount of or magnitude of voltage which is hitting the primary winding of the transformer is reduced. In that way, we can able to safeguard the transformer primary winding. In that way, we can able to assume that that is an advantage of a corona. Then, how to reduce the corona, or what are the various ways to reduce the corona? In the sense, there are two ways only. By increasing the conductor size, and there are obviously we have to see that once if I am saying that it is increasing the conductor size, we have to see in the other direction. Is there economically feasible, or that Kelvin's law is getting satisfied? These are the things you have to see. Then by increasing the conductor spacing, the next one is by increasing the spacing between the conductor as greater as the diameter of the conductor. If you do that, the problem is once again the span distance increases, the amount of cost which we are spending for the transmission line increase. This will increase the overall cost of the transmission line. So once again, check the feasibility. All these things are coming under power system economics point of view. Yes, these are some of the numericals which is based on the corona that we have to see. And there are something called the Ferranti effect in a transmission line. What is the Ferranti effect in the sense? The Ferranti effect is a rise in voltage at the receiving end when compared to sending end at some particular condition. So which causes that high voltage at the receiving end? Suppose if I am sending 11 kV in the primary or the sending end, if we go and measure after 10 km or 20 km, definitely the voltage will be less than that. If it is 11 here, it may be 10.5 kV, 5 kV. But there are some conditions where you are getting, if you send 11 kV at the sending end, if you go and measure the receiving end, it may be 11.2 or 11.3 kV. The reason behind that is called the Ferranti effect. This effect is due to lightly loaded transmission line, or if it is a new transmission line that if you are going to erect it. There are so many capacitors exist between the transmission line. Each and every capacitance will form a charging current. The charging current will support some amount of voltage and will be leading the voltages which you apply, so that these charging current, these are virtual capacitors in the transmission line which causes charging current, and that will increase the voltage at the receiving end. So that we have taken care. Power flow through the transmission line. To find the power flow in a transmission line, it's a bidirectional flow. Okay, like Vs is equal. These are the two formulas. You know that Vs is AVR plus VIR, which is the equation of your generalized circuit constant. From there you have to derive it. Write the expression for PR plus JQR, where PR is the receiving end power, QR is the receiving end reactive power. If you find that, you are getting Vs into VR by V angle beta minus alpha minus AVR square by V angle beta minus alpha. Okay, so here we consider that alpha, betas are the constants coefficients or angle of the constants. A, B, C, D are the constants. A at an angle of alpha, B at an angle of beta. From there you have to consider. If you see this, Vs is the sending end voltage, VR is the receiving end voltage. Both these voltage should be a line value. But substituting that, both the values should be line value, and B is the equivalent impedance, which is normally in terms of ohm. Then if you divide that into a real part and imaginary part of the previous expression, if you see this expression, if you find the real part of this and then reactive part of that, we have two expressions. One is for receiving at real power, other is the receiving at reactive power. You can see that if you operate with cosine term, it is the real power of the receiving power and reactive power of the receiving power. So from there we can able to draw the circle diagram to understand the various quantities. Yes. So the power circle diagram. This is an important topic to find the various. This is a graphical representation of the system. This is used to find the various parameters. Suppose there are using a circle diagram. The power circle diagram is a graphical representative and used to determine the capacity of VAR devices. VAR in the sense how much is the capacitance are to use. Okay.